Math 1332, Chapter 10, Probability and Counting Techniques, Section 2, the Fundamental Counting Principle, Permutations. Video 1, the Fundamental Counting Principle. Now, if you stare at that phrase too long, I think I know what you're going to start saying to yourself. Why do we need a fundamental principle to count? I know how to count. Well, I'm glad you can count. So can I, probably higher than you. Well, it's nothing personal. But I know the names of numbers up to 66 digits long. And don't just say Google, which is one followed by 100 zeros, because there's a lot of numbers between 66-digit long numbers and a Google that I don't know the names of, but frankly, you probably don't either. But if you actually know how to read a number like 62 decillion, 325 nonillion, 560 octillion, 980 septillion, 123 sextillion, 142 quintillion, 456 quadrillion, 968 trillion, 111 billion, 23 million, 143,125 without looking it up, then kudos to you. But sometimes, kidding and showing off aside, but sometimes we need to be able to count how many ways something can occur without physically listing them out. For example, let's say you want to order a meal at a restaurant. They have a special, one appetizer, one entree, one sides. I think it was originally two sides, but I changed it. One appetizer, one entree, one side, one bread, and one dessert of your choice, all for $9.99 plus tax. So let's say after taxes and tip, it's $12.50, which is standard tax rate plus 15% and a little bit to round it up, $12.50. And here's the list of things you can choose from. 4 appetizers, I'm not going to read them to you. 4 entrees, 6 sides, 2 breads, and 3 desserts. The restaurant offers a $5,000 prize to the first person who eats every possible meal over the course of a year, limited to 2 meals per day, lunch and dinner. Oh, by the way, this promotion is starting on January 1st at this fictitious restaurant. Let that sink in. If you can eat every possible meal from this list by choosing one from each category and be the first person to do it over the course of a year, $5,000 for you. Can you do it? Well, how many meals is that? Good luck listing all of them. It's not impossible. It's just impractical. So how do we do something like this? Well, let's start smaller to build a strategy. This is a common problem-solving tool, not just in math, but in life, to work out a smaller but similar problem and then try to develop a technique to apply to the original larger problem. So we're actually going to go through the process of developing a technique, polishing it off, and at the end it'll be called the fundamental counting principle. So how can we do a smaller problem? Well, what if we just had to pick an entree and a bread? We have 4 entrees to choose from: steak, chicken, pork chops, and fish. And we have 2 breads, biscuit and roll. Let's see if we can list them all. And it's really not that hard to do, because, and I think we're going to type these. I can type faster than I can draw sometimes. It's really not that hard to do in this case, because let's say you pick steak. Well, I only have 2 choices for a bread: a biscuit or a roll. So there's 2 meals. But let's say we pick chicken. Well, same thing. We can either pick a biscuit or we can pick a roll. Or if we pick pork chops, new meal, pork chops. Copy this. We can either pick a biscuit or we can pick a roll. Or we could pick fish. Let's do this so we can see everything. There we go. We could pick fish with a biscuit, or we could pick fish with a roll. Well, that wasn't too hard. We've listed all of them, and we listed them in a systematic way by picking an entree and then going through the breads, picking the next entree, going through the breads, and so on and so forth. Notice that there's there are 2 meals here, 2 meals here, 2 meals here, and 2 meals here. Because for each meat, we had 2 choices of bread. For each entree, we had 2 choices of bread. And notice that there's a total of 4 pairs because each pair focused on a certain entree. So no matter how you slice it, there are 8 possible meals we can make here based on the fact that there were 2 breads and 4 entrees. Wonder where the 8 came from. Seems the number of meals we could make if we just had to pick 1 out of 4 entrees and 1 out of 2 breads is 8. Clearly 4 times 2 is 8, but does this always work? You got to be real careful making a generalization off of one example, especially one simple example. There's a thing in mathematical logic beyond what we talked about that basically says you can have a finite number of examples that say one thing, and it doesn't prove that it always works. It's impossible to make a generalization from a finite number of examples. The probability your generalization is right increases, but let's not get into that. All right, so does this always work? Well, what if we picked 1 of 4 entrees, 1 of 2 breads, and 1 of 3 desserts? Let's think about this for a second. When it was 4 entrees and 2 breads, we said 4 times 2 was 8. That gave us the correct number of meals. What if we threw in 3 desserts? What do you think we would get? Could we list them out? Could we list them out again? Well, we could, but we can actually figure this out without listing all possible meals, and here's how. We already know that there's 8 possible meals we can choose by creating an entree and a bread. They're listed on the previous page. For each of these, we have 3 choices of desserts. So imagine, and give me a second to clean this up. All right, now that we got that cleaned up, let's imagine that we get to choose a third dessert. Choose a dessert, and we got 3 desserts to choose from. Well, for this guy, we could put one of 3 desserts on it. What were the desserts? Cherry pie, chocolate pie, and brownie. We'll just call them desserts A, B, and C. So for this one, we could do that with dessert A, we could do it with dessert B, and we could do it with dessert C. So for that meal, there's 3 other ways we could tack on a dessert. And the same thing for all of these. I can make 3 meals with that plus dessert, 3 with that, 3 with that. And each of these I could do 3 times over. So it stands to reason that we're going to get 8 times 3 meals, and you would be correct, 8 times 3 being 24. Using the same approach as before, not a porch, not a porach, whatever that is. Using the same approach as before, I swear I'd proofed this before I started, there would be 8 times 3 equals 24 meals. But remember that the 8 came from 4 times 2, and so we could think of it as 4 times 2 times 3 meals. So in other words, when we had a choice of 4 entrees, 2 breads, 3 desserts, there were 4 times 2 times 3 meals. Does this always work? The answer is yes, and it's called the fundamental counting principle. Theoretically, it sounds something like this. Suppose an event consists of making a sequence of decisions, plural, a sequence of decisions. For the first decision, you have N1 choices. Now that 1 is supposed to be a subscript like this. I just can't type subscripts in here. For the second one, for the second decision, you have N2 choices, and for the third decision, you have N3 choices. And again, all of those are supposed to be N's with subscripts, N1, N2, N3. I think I can copy and paste it from Word into here, but I'll just write it. So, and by the way, it can be more than 3 decisions, which is why there's an etc. down here. Then the total number of ways you can make all of your decision. Why do I not want to pluralize the word decisions? Then the total number of ways you can make all your decisions is the product of the individual number of choices. In other words, N1 times N2 times N3 times etc. And we can count the total number of ways to make these decisions without listing them all. It worked here. 4 times 2 was 8. It worked there. 4 times 2 times 3 was 24. And it's going to work in the original problem. Going back to the original problem with choosing the meals, we have to make the following decisions. Choose 1 of 4 appetizers, 1 of 4 entrees, 1 of 6 sides, 1 of 2 breads, and 1 of 3 desserts. The fundamental counting principle says we can count the total number of meals by simply multiplying all of these numbers. There are a total of 4 times 4 times 6 times 2 times 3, which equals 576 different meals. So, could you win the $5,000? Remember, the restaurant is offering a $5,000 prize to the first person that eats all the different combinations of meals starting on, we'll say starting on January 1st. So could you win that? Well, there's only 576 different meals, but you better not plan on eating one per day, especially if you want to be first. Yes, to be the first person to do it, you'd have to start on January 1st and eat lunch and dinner there for 288 days straight. That's half of 576. That would put it through October 15th in a non-leap year, October 14th in a leap year. So could you do it? Yes, of course. Remember, each meal averaged out to $12.50 after taxes and tips. You'd have to spend 576 times $12.50 equals $7,200 to do it. And you might be thinking, yeah, but I'm still getting all the meals and then $5,000 on top of it. Would a restaurant do this? I don't know. It'd be a logistical nightmare to keep up with, although not impossible if you put your mind to it. So to summarize, the fundamental counting principle says, if you got a sequence of decisions to make and each decision has so many choices, then the total number of ways to make all of your decisions is the product of those numbers of choices.